Notes 9.8 are on power series. Up to this point, we've considered only series of constants. In this section, we begin talking about series that are actually functions. The purpose of doing this has to do with approximating a curve. I'm going to sketch the curve of sine. Now, one of the tasks we will have is to find a polynomial function that fits this curve. If we start with the line y equals x, that would look like this. Now that only matches the sine curve for a very short moment. It's basically tangent to the curve, or looks tangent to the curve at x equals 0. If instead we choose to use a quadratic to try and mimic the sine curve, we end up with something that's way off. That does not look like the sine curve at all. So we try another polynomial. We try x to the third power. X to the third power looks like this. So it starts to have the shape of the sine curve, but it's kind of in the opposite direction. Instead, what if we took the opposite of x cubed? So now we would be decreasing, then increasing, then decreasing. So for a very short while, but better than y equals x, we match the sine curve. So where the sine curve matches the negative x cubed curve right in there, that's where they're converging on one another. That's where they match up. So we're going to call that an interval of convergence. And eventually we're going to look at whether that includes the endpoints of that interval, if the endpoints are included in the interval of convergence or not. And the other thing we're going to look at is if we have that interval of convergence, what would the radius of convergence be? So when you're in the middle of the interval, how far out is it to the endpoints of the interval? So here we start a power series. The power series has a constant, and then it has terms, x to the first, x to the second, x to the third, and as many terms as we would need to approximate the function that we are working toward. And that's why it's termed a power series. All of the terms are powers of x. So that's why we talk about a power series, powers on x. The way it is written here, we simply have an x squared, an x cubed. But the convergence that occurs is not always going to occur around the origin. If we have another curve and we look for convergence, we might have a polynomial that converges with that function out to the right of the origin, let's say. So this could be our interval of convergence, and it would be centered about some other point. So let's say it's centered around x equals a. If it's centered around x equals a, then our series has to be written with c sub 0 plus c sub 1 times x minus a to the first plus c sub 2 times x minus a to the second, and so forth. So the interval of convergence can occur off to the right or left of the origin. And when that happens, we want to represent it like this to indicate it's not centered around x equals 0. If you determine a fixed number x and you substitute that into the series, the equation becomes a series of constants, and then we can test for convergence or divergence on that series. A power series may converge for some values of x and diverge for others. So that is the interval that I'm referring to. Over that interval, we would have convergence, and then for the rest of the function, we would not. The sum of a power series is a function whose domain is the set of all x for which the series converges. If we set up an example where we just let the constants equal 1 for all n, and we write the above power series as a geometric series. Let's do that. So I'm going to rewrite the power series as a function, and I'm going to let the constants equal 1s. So c sub 0 would be a 1, and then the next term from up above is just 1x, and then the next term is just 1x squared and 1x cubed, and so forth. You know that this is the power series as n goes from 0 to infinity of x to the n power. What is your common ratio? Do you see that the common ratio is x? So that means this series converges when absolute x is less than 1. By the way, that means when x is between -1 and +1. So that's how we would write this absolute value inequality. We would write it this way as a regular inequality. We also know that it diverges when absolute x is greater than or equal to 1. Notice, if we let x equal 1/2 in the series above, we get this series right here, this geometric series, and it is convergent. Notice that x equals 1/2 is when absolute x is less than 1. However, if we let x equals 2, now absolute x is not less than 1, and we substitute in 2 for all the x's, we get this series. This series is geometric, but it is divergent. In general, we write the power series with this formula, and I mentioned this setup where we consider that the series is not centered at the origin, that it's centered somewhere else at x equals a, and it is called a power series about a when we do that, or a power series centered at a. Notice if x did equal a, all the terms go to 0 for n is greater than or equal to 1, so it would always converge at x equals a. A new theorem we have is the following. When you have a power series, there are only 3 possibilities for that power series. The series might only converge when x equals a. I compare that to the story where when we had the sine function and we tried to fit the line y equals x, and it pretty much just converged at x equals 0, meaning it just intersected at x equals 0. We would say it converges only when x equals a. The second possibility is that it would converge for all x. So our polynomial might be a perfect fit to the curve, and it would converge all through the domain of the function. And then the third possibility is that it only converges for a little while. I will try again to sketch this sine graph. And if we had a third-degree polynomial, and that third-degree polynomial had the right coefficients so that it went like this, okay, it's a little wobbly, but from about here to about here, the blue curve and the red curve are on top of each other. That's your interval of convergence right there. And it's centered, well, it should have been centered about 0. I know my sketch doesn't depict that very well, but that one looks centered about 0. And you would talk about being from the center out to the endpoint as a radius of convergence. So you might be asked, what's the radius of convergence? Or you might be asked, what's the full interval of convergence? The interval of convergence consists of all the values of x for which the series converges. In the first case up above, it was just a single value a. In the second case up above, the interval of convergence was all reals. And in the third case, we would come up with that interval as an inequality. When we talk about that interval of convergence happening, you know that the second curve was kind of pulling away at the ends of the interval of convergence. Sometimes it looks really solid, like the end of the interval is part of that and it looks like it's convergent too, but there's other times where the endpoint of the interval of convergence is not part of the convergence. So what we're going to have to do is check the endpoints. And this is where your talents of checking for convergence and divergence of series will come in handy. Let's do an example. My first example has powers of n. I'm going to use the ratio test to address this question. Let's set up a limit, and that will be the quotient of the n plus 1 term with the nth term. So x minus 2 to the n plus 1 over n plus 1 times 3 to the n plus 1. And then I'm just going to copy our series in the denominator. I want to rewrite that complex fraction as the product of two fractions. So when I do the numerator, I'm going to break it down. So x minus 2 to the n plus 1 power, that's x minus 2 to the n power times x minus 2 to the first power. So I broke that down. In the denominator, I'm going to copy the n plus 1. And 3 to the n plus 1 breaks down into 3 to the n times 3 to the first. Now I'll flip the bottom fraction. Now I can do some canceling. Cancel the x minus 2 to the n power. Cancel 3 to the n. This limit is on n, so we do not need to keep the 1/3 inside of the absolute value. We don't need to keep the x minus 2 quantity there. So bring out the 1/3 and bring out absolute value of x minus 2, because we're only taking the limit on n, not on x. What's left inside is an n in the numerator and an n plus 1 in the denominator. Do you remember how we would handle that limit? I'll set it up just in case. We would divide top and bottom by n. So we would get 1 over 1 plus 1 over n. And the limit on that would be 1. So we get 1/3 times the absolute value of x minus 2 times 1. Now, by the ratio test, the series converges if this 1/3 absolute x minus 2 is less than 1, and diverges if 1/3 absolute x minus 2 is greater than 1. So we just want to look at when it's converging. Therefore, I'm going to look at this inequality. Solve for x in this inequality. The first step would be to multiply both sides by 3. That would give us absolute x minus 2 is less than 3. By the way, in this step right here, when you have an absolute value isolated like that, that's actually giving you your radius of convergence. So this means r equals 3 when I get to this step. Even though I'm not done yet, I can see the radius of convergence. This means the radius of convergence is 3. Now, to remove absolute value bars from this inequality, this is a less than. This is an absolute value inequality with a less than. So that to take away the bars means to rewrite it as the quantity x minus 2 must be in between 3 and negative 3. The absolute value symbol means distance from 0. So when you see the absolute value of something is less than 3, that means it's less than 3 units from 0. So when we write this new line, that's letting you know it's in between negative 3 and 3, which is less than 3 units from 0. The last step is very easy. You're going to add 2 to get x by itself. Just add it in all 3 parts of the inequality. So we get negative 1 is less than x is less than 5. That is your interval of convergence. The problem is I need to check the endpoints of that interval. The first endpoint is x equals negative 1. In order to check this endpoint, I'm going to go back to the original series up at the top, right up here, the original series, and I'm going to substitute negative 1 in for x. When I substitute negative 1 in for x, I get the quantity negative 3 to the n power. So the series becomes negative 3 to the n power over n times 3 to the n. This is an alternating series. So when I look at part 1 of the alternating series test, I'm looking at 1 over n times 3 to the n compared to 1 over n plus 1 times 3 to the n plus 1. Can you tell that the denominator of our term is less than the denominator of the next term? So that means our fraction is greater. Part 2 of the alternating series test will take the limit as n goes to infinity on 1 over n times 3 to the n, and that equals 0. So this series converges by the alternating series test. That means this endpoint is included in the interval of convergence. Now let's check the other endpoint of the interval, which is positive 5. Again, I'm going to take positive 5 and substitute it back into the original series up here. 5 minus 2 is positive 3. So I'm going to rewrite that as positive 3 to the n over n times 3 to the n. Do you notice that the 3 to the n's cancel, which makes our series 1 over n? This is the harmonic, which is divergent. So that means this new series is divergent, and that means the interval of convergence does not include this endpoint. All right, therefore, the interval of convergence includes negative 1, but it does not include 5. So that's our interval of convergence. And do you notice when you go from negative 1 to 5, that's 6 units long? Well, if you're in the center of that interval, The center of that interval would be at x equals 2. Then the radius out to the endpoints is 3. And remember, back up here in one of these initial steps, we noticed that the radius of convergence is 3. Our next example has factorials and powers of n. So that means I'm interested in doing the ratio test. I'll set up the ratio test. Break up 2 to the n plus 1 into 2 to the n times 2 to the first. Break up x to the n plus 1 into x to the n times x to the first. Break down n plus 1 factorial as n plus 1 times n factorial, and then we're going to flip the bottom fraction. Let's cancel 2 to the n's, x to the n's, and n factorials. The 2 and the x are not part of the limit. The limit is on n only. I'm going to move 2 and absolute x out in front of the limit, and I'm left with 1 over n plus 1. The limit as n goes to infinity of 1 over n plus 1 is 0. So we're getting a 0 result. Remember, when you do the ratio test, you compare your result with 1. 0 is less than 1. That means by the ratio test, the series converges for all x. So if the series is converging everywhere, that means it is infinity, and the interval of convergence is all reals. Our next example has factorial and powers of n. I'll set up the ratio test. I'll break up the n plus 1 factorial. The x to the n plus 1 is x to the n plus 2. So that breaks up as x to the n times x squared. N factorials will cancel. X to the n's will cancel. One of the x's will cancel. We're about to take the limit as n goes to infinity, which does not involve x. So we'll remove x from the limit and just take the limit as n goes to infinity of n plus 1. That limit goes to infinity, and comparing that to 1, it is greater than 1. By the ratio test, the series diverges for x not equal to 0. The given series only converges for x equals 0. Therefore, the radius of convergence is 0, and the interval of convergence is 0. Our last example is number 14 from the book. I'm noticing a power of n. I'll set up the ratio test. I can remove x from the limit. I'm going to divide the numerator and denominator by n. The limit as n approaches infinity is 2 over 2, or 1. By the ratio test, the series converges for absolute x is less than 1. Just to point out again, notice you can see the radius here. The radius of convergence is 1 when it's written in an absolute value inequality like that. So the absolute value of x has to be less than 1. And when I remove the absolute value bars, that means negative 1 is less than x is less than 1 is the start of our interval of convergence. But we still have to check the endpoints to see if they're included. So this could be negative 1 is less than or equal to x is less than or equal to 1, but we have to check. So let's first check when x equals negative 1. When x equals negative 1, I'm going to substitute negative 1 in for x in the original math problem up here. So x is in the numerator and that gets us negative 1 to the n power over 2n minus 1. Notice that we have an alternating series in this. So if I check condition 1 of the alternating series test, I will be checking 1 over 2n minus 1 compared to the next term. So the next term is when I plug in n plus 1 for n in our nth term. So I'll rewrite that simplified. In the denominator, 2 times n is 2n. 2 times 1 is 2, minus 1 is positive 1. So I'm comparing these two fractions. Now our term has a denominator less than the comparison term. So if our denominator is less, that means our fraction is greater. So therefore, the next term is less than or equal to the nth term. So we have decreasing. Condition 2, let's take the limit as n approaches infinity of 1 over 2n minus 1, and that is 0. So both conditions of the alternating series test are satisfied. Therefore, the series converges when x equals negative 1. That means negative 1 will be included in the interval of convergence. Now let's check when x equals positive 1. Substitute positive 1 in for x. We get 1 to the nth power over 2n minus 1, which is just 1 over 2n minus 1. I'm going to compare that with the 1 over 2n series. Our denominator is smaller, which makes our term bigger, and 1 over 2 to the n is a p series with n equals 1. So it's divergent. Or you could say it's the harmonic. You could say it's the harmonic, so it's divergent. This means the series diverges when x equals 1. I'll have to go up here for more space. Therefore, the interval of convergence is negative 1 to 1, including negative 1.